Chemistry. Thermochemistry is basically the study of energy flow in chemical reactions, chemical processes. So we're talking about energy. That's the main thing. So we have to be sure what we're talking about. You guys know what the definition of energy is?
The amount of, I can't say energy. The amount of whatever it's making the.
Okay, so
Ability to do work.
that's I mean, if you replace whatever with something, it's not that, right? Anybody else know like the real definition?
Work being done?
What's it?
Something with work?
Yeah, it has something to do with work, which is what Chris was describing. You know, that's work, right?
Is it work?
Okay, so energy is the capacity to do work. So you know, the whatever is the capacity, but that actually that was not bad. And Sam's right too. Sam, you're the one that brought up work, right? So do you know the definition of work? What's that?
You'd like to find it like the amount that you can displace?
You're on the right track. Anybody know the official definition? It's like you're right when you say money. Work. It's force applied over a distance. Okay. So, for instance, to lift a 200-pound barbell from the ground to over your head, you have to apply a certain force, right? You have to, that force is going to be, and you guys remember the definition of force, right? Yes? What's the definition of force? Mass times acceleration, right? So when you're lifting up that 200-pound barbell, okay, the mass is, the mass of the barbell. What's the acceleration?
Speed.
Velocity isn't acceleration.
Delta.
You said delta.
Right here.
You're right. Delta what?
X. I remember. Delta 7 was.
So you're thinking, well, delta pressure is good. So the change is the delta, right? Or if you had calculus, it's the d, dv dt. This is e. So acceleration is change in velocity over change in time. I guess I should ask, do you know what the velocity is? What's the definition? You had actually, Elizabeth, you were, I think, giving me a definition of velocity.
I was.
Well, what did you say, remember?
In position, something about
Yeah.
position and motion.
Speed which you change direction.
And this is all in English, right? We can do it in symbols. It's the same thing. It's what it means, right? Velocity is change in position with respect to time, or over changing time. So, energy is the capacity to do all these things, to apply a force over a distance. Applying a force means you're accelerating mass, which means you're changing its velocity with respect to time, which means you're changing its position with respect to time. Change of position with respect to time. So going back to that barbell, the force that you have to apply to pick it from the ground to over your head is the mass of the barbell times the acceleration. And imagine picking it, you don't want to do this, but picking it up infinitesimally slow, to where you're not making it go any faster. You pick it up at some speed and it stays the same speed all the time, so its velocity isn't changing. Right? You still have to apply a force, right? Which means there's still some acceleration in there somewhere. You guys know what that one is? How about gravity? you know the acceleration due to gravity? 9.81 or so meters per second squared. You guys know that one? That's the no. Okay. So gravity accelerates stuff, right? If I let go of this, what's going to happen to it? It's going to fall. It's not moving now, right? In our frame of reference, it isn't moving. Its position isn't changing. It doesn't have any velocity. But if I let go of it, it's going to move that way. You guys all know that, which means its position is going to start changing, which means it has no velocity now. It's going to have some velocity, so its velocity is changing. It's accelerating, right? That's due to gravity. It's 9.81 or so meters per second squared. That's the force that we're talking about here with picking up that barbell. So I'd have to apply a certain force to it, but I do a different amount of work if I just pick it off the ground and pick it up to my waist, or if I pick it up from the ground and pick it up over or put it over my head, right? I move it. It's the same force, but it's applied over a different distance, right? So it's more work to lift it over my head than it is to just pick it up to my waist, right? So that's what we're talking about here. And in order to do that work, I'd have to have energy. I'd have to have the capacity to do that work. Now, in the context of chemistry,
So the smaller the force.
so now we're not talking about barbells anymore. We're talking about chemical reactions, gases, things like that, solutions. We use U to symbolize what's called the internal energy of a system. And it's simplest, I think, if we start out thinking about just some gas in a cylindrical container. Do you guys know the kinds of energy, the two basic kinds of energy that we deal with? Kinetic and
Potential.
potential, right? Yeah. So when we talk about the internal energy of the system, say gas, right? We're talking about all of the kinetic energies and the potential energies in that system. Even for a really simple gas, say a balloon filled with helium again. Right? That gas, okay, each of those particles is going to have a kinetic energy depending upon, how fast it's moving. We're assuming, forgetting about isotopes, we're assuming they all have the same mass. But they're going to have different distribution of speeds. You guys know about that, which means they're going to have a distribution of kinetic energies. There's also going to be, so each one of those is going to have its own kinetic energy. And it's also going to have potential energies, right? The potential energy could be from the interactions between the real particles as they come close to each other. Could be between the electrons and the proton in the protons in an atom. There's all kinds of different energies, right? And even in a small system of just regular sized balloon filled with helium, it's going to be, 10 to the 23rd or on that order atoms. It's just way too complicated to individually measure their kinetic and potential energies. But what we can do, that's one of the nice things about thermodynamics and thermochemistry, is we can measure macroscopic properties, like temperature and things like that, and get a handle on microscopic properties. And that's the connection, by the way, between the macroscopic and microscopic. Microscopic's quantum, pretty much, right? Macroscopic is pretty much what we're going to talk about in this chapter, thermodynamics, thermochemistry. There's a field, we don't talk about it here, it's called statistical mechanics, that it connects the two. So, there's two ways that we can change, it ends up, the energy, the internal energy of the system. And that is through work, what I've just described for you, doing work on the system, applying a force over a distance on that system, or what's called heat. We say that's actually the first law of thermodynamics. And I'm going to talk about each of these terms a little bit first, okay, because we're going to use them. Give you a rough idea, though. Heat it's the means by which what we call thermal energy is transferred. Work I've already defined for you, force times distance. Right? So now we don't have to go inside that balloon of helium and measure the kinetic energy and the potential energy of each of the particles and their reactions with each other, interactions with each other. We can measure heat, we'll talk about that a lot in this chapter, and the work, add them up, and we know what the total change in internal energy is for that system. So let's go back and talk a little bit more about work. And that's the reason that we're talking about work, is the first law of thermodynamics right here. Yeah.
Delta U is the U capital or lowercase?
Capital. And that's important, actually. Later on, I'll talk about state functions and energy transfer functions, and state functions are capital, energy transfer functions are lowercase. I'll get to that later. So to talk about work, we're going to imagine a cylinder, and this cylinder has a piston in it. This piston has no mass, and there's no friction. So we're going to take this piston in this cylinder, and we're going to add mass on top of it, though. We're going to add weights, so we know how much mass we're putting on there. And what's going to happen, okay, so it's, first of all, there's some gas in here. So we put this piston on there, put a little bit of weight on there, and it's going to compress that gas until it can't compress it anymore, and it's just going to float there, right? You guys got that picture? It's going to be at some height, so that's where it is right here. The initial height. Then we're going to press on the piston, compress the gas. So now it's going to be lower, right? Final height. The work, force times the distance, the distance they travel is just final minus initial, right? Call that delta H. Force, let's look at it this way. In the last chapter, in the gas chapter, we talked about pressure being force over the area. Remember that? So we can rearrange this a little bit. Force is the pressure exerted times the area. That's nice because if we put it up in here, force is pressure times area, distance is delta H. But for our cylinder here, okay, the area, you can't see it because this is a two-dimensional drawing, but the area is the surface area of the piston. And so if it's a cylinder, the area times the change in height, you guys know what that is? What's that? What's the, for a cylinder, what's the area times the height? Volume, right? You guys know that? So we can write this, because it's changing, it's a change in volume, right? So the work is pressure times the change in volume. You guys okay with that so far? Well, we have, in chemistry, we have a sign convention, positives and negatives. And our convention is that we view everything from the point of view of the system. The system in this case would be the gas inside of the cylinder. And so if work is done on that gas, we want that to be a positive value, positive quantity. If work is done by the system, it's losing energy, so we want to have the work be a negative quantity. That makes sense to you guys? So to make that consistent, okay, here, this volume is less than this volume, so this delta V is negative, right? But we want this work to be positive because work is being done on. You have to do work on that system to compress it. You guys buy that? We want work to be a positive value in this case, so we throw a negative sign in here. Like that. So and that's nice because pressure is something that we can measure easily at the barometer or something. Delta V is something also we can measure. Now, we want work to have the units of energy, something like joules or something like that, which is what you get if you have pascals for the pressure and cubic meters for the change in volume. But most of the time, kind of problems that we do in here, the pressure isn't in pascals, it's like in atmospheres, and the change in volume is usually in liters, right, not cubic meters. And so there's a conversion factor you're going to want to know. There's a unit of work called the liter atmosphere. If this is in liters, this is in atmospheres, then the units would be liters atmospheres. But to convert it to joules, you just use this conversion right here. 1 liter atmosphere is 101.325 joules. Memorize that?
So that's from pascals to what again?
That's from liters atmospheres to joules.
Oh, you're right. Pascals are always 18 atmosphere.
They're different measures of
So
pressure.
you have to convert pascals to atmosphere. And atmosphere to
What he's saying is that most of the time when we do these equations, we'll have atmospheres per liter instead of pascals per.
so pascals have pictures like that. Looking to
Yeah. Basically, yeah. You just know that conversion.
You get that?
Yeah, I got it. Right.
Pascal for?
Are we able? No,
Is
not
it?
really.
Not really? It's okay. If pressure's in pascals, pascals per cubic meter actually.
Okay,
And
right.
the volume changes in cubic meters, and basically we get joules.
All right.
No? No? Let me,
It's okay. I'll get it.
no, because you're not getting
Pascals
this.
per meters.
Let's go. You have a book here?
So, for example, like you would have it as, you're going to do an example right now, so I'll just look at what you do with it.
If you look on page 434, table 13.2, one of those ones that you memorized for the gas laws. Yeah,
Oh, I forgot.
gives you units of pressure in pascals.
Mhm.
Okay.
That's beautiful.
So, okay, the upshot
Oh,
of
okay,
it
I
is,
see.
when you're
Oh.
calculating work, and I'm going to do an example and show you right now. If you get, thank you, if you get units of liters atmospheres,
Mhm.
and you want joules, use this as a conversion factor.
All
That's
right.
the important thing.
Okay. Thank you.
So for example, we want to calculate the amount of work done by a gas that expands from a volume of 1.93 liters to a volume of 11.41 liters against a constant pressure of 1.10 atmospheres. We just use that equation over there. Before we can do that, can you guys tell me if the work is going to be a positive or a negative number, value, quantity?
Negative?
Is the system is the gas. Is it doing work or is it having work done on it?
It's doing work.
It's doing work. In that case, it should be negative, right? It's losing energy, right? It's expending energy to do that work, right? It has to lift up that piston. So work is, we use minus P delta V. Make sure you remember that negative sign. It's a common mistake to prevent. Pressure is constant, right? So it's just, so the pressure on top of it stays the same. It's just pushing against that pressure. It's 1.10 atmospheres. And the change in volume is just the final volume minus the initial volume. We get minus 10.4 liters atmospheres. I asked it in joules, so we're just going to convert it. So to convert from liters atmospheres to joules, multiply it by 101.325. Get negative 1.05 or 1.06 times 10 to the third joules, which is the same as negative 1.06 joules. The kind of work that we're talking about here, the only kind of work we're really going to deal with is called PV work, pressure volume work. So remember, okay, we're talking about internal energy. I showed you the first law of thermodynamics. The change in internal energy is equal to Q plus W. This is the W term. Now we're going to talk about the Q term. said, is the means by which thermal energy is transferred. When I say thermal energy, the best picture I think to have is to think about a gas and the kinetic molecular theory of gases, where imagine a balloon inside a gas inside of a balloon, and when we were talking about gases, we assumed that all the collisions were elastic, no energy was lost. But in real life, okay, if those particles of gas inside that balloon, as they hit the wall of that balloon, some of that kinetic energy is going to be transferred to the wall, to the molecules in the material that makes up the balloon. You guys buy that? It's kind of like pool balls, right? The cue ball hits another ball, some of the energy gets transferred. And so what happens then is there's more kinetic energy in the balloon itself, not the gas inside, but the balloon. It's moving faster, right? And then, so some of that energy was lost, it got transferred to the air. That's thermal energy, and that was transferred. What happens then is as molecules of air, nitrogen, oxygen, carbon dioxide, what have you, hit or come in contact with the outside of that balloon, some of that kinetic energy, that thermal energy, is transferred to the air. Right? That makes sense? So that's what we're talking about. Heat is the mechanism or the process, the means by which this happens. It works for a gas, it works for a liquid, it works for a solid. Right? All basically the same idea. We have motion, we have kinetic energy. And that kinetic energy gets transferred from one particle to another, from the system to its surroundings, is what we say. And that's what we're talking about when we say heat. Okay? You guys probably already know these terms, but okay. Q is positive. Q is greater than 0. We use the same convention as we do with work. Do you think then that thermal energy is going to be transferred into or out of the system if Q is positive?
Into.
Into. It's gaining energy. Good. Call that process, where Q is positive, we call it an endothermic process. Because thermal energy is going into the system. Q is less than 0. That's just the opposite. That means that thermal energy is being lost by the system. We call this exothermic. So when you hold an ice cube in your hand, right, it feels cold, right? It gets colder. From the point of view of the ice cube, is that exothermic or endothermic?
Exothermic.
Endothermic. It's absorbing the heat.
There's some disagreement out there. So
It's endo, according to the
Isn't
ice
it
cubes, it's
absorbing?
gaining
Absorbing,
energy.
sorry.
yeah, why does it feel cold?
Okay.
It's exothermic to your hand.
Because you're losing energy, right?
Yeah.
So your energy, the energy from your, thermal energy from your hand is being sucked into that ice cube, right? So the ice cube's gaining thermal energy. So from the point of view of the ice cube, that's an endothermic process. Q is positive for the ice cube. It feels cold to you, right? Because for you, it's exothermic, right? You hold your hand over a flame, it feels hot, right? The flame feels cold to itself, if it could feel, right? Right? Because it's losing energy, right? That process, combustion, is exothermic. You really got to think about science and thermochemistry, right? Just, I want to start from the beginning, make sure you guys are thinking in the right directions. All right, so that's exothermic and endothermic. I already gave you the first law. Let's put it right there. State functions.
What does U represent in that equation again?
We're changing internal energy. Or U is internal energy. Delta U is a change in internal energy.
Okay.
So first of all, delta U is what we call a state function. I'll explain that in a moment. Q and W are not. They're not state functions. They're what we call energy transfer functions. And the convention that we use is that state functions are capital letters. Delta U, P, V, and T in the ideal gas law. Those are state functions. And we use lowercase letters for energy transfer or non-state functions. Are just, in general, non-state functions. So a state function is a function whose value depends only on its current state and not how it got there. For instance, my height above sea level, my elevation above sea level, is a state function because it doesn't matter how I got here. Imagine going up to the top of Half Dome, right? Yosemite. When I'm up there, whenever I get up there, my position, my height above sea level doesn't depend at all how I got there. It's a state function. But the amount of work that I had to do to get there, that's a state function. Depends upon the path I took. If I drove to the airport, hopped in the helicopter, have them fly me over there, and then drop me off right on the top, not much work I'm doing. On the other hand, if I ran around the world okay, all the way around the world to the other side of it, right? Ran around the base of Half Dome a bunch of times. Then I climbed up the back of it. I did a lot more work, but I ended up at the same place. Right? So the work that I did to get there is not a state function, it's an energy transfer function. But I ended up at the same place. So my height above sea level, my elevation, that's a state function. You guys get that? So in terms, back into thermochemistry, internal energy, change in internal energy is a state function. Its value only depends upon the current conditions, not how they got to be there. But Q and W, heat and work, they do depend upon how you got there. I like, your book has a good analogy that I haven't seen in the general chem text before. Q and W are kind of like rain, right? If you have a barrel that gets filled when it rains, right? You don't say that there's rain in the barrel, right? You say there's water in the barrel, right? Rain is just the means by which the water got into the barrel. Just like we don't say we have heat in the system, we don't have work in the system. But heat and work are the means by which energy is transferred into a system. You guys see that? That's a good analogy. So heat isn't a state function. But a lot of times in the lab, what we're measuring is pretty much heat, right? And that's a problem because it depends upon the conditions. It's not something that we can tabulate, that we can compare, unless the conditions are exactly the same. So a long time ago, we came up with this function called enthalpy. Symbol is capital H. That means it's a state function. Capital H. The definition is that. It's the internal energy plus PV, pressure times volume. It ends up that we never, ever talk about just the enthalpy of anything. We only look at the changes in enthalpy. This is the form, the definition of enthalpy that we use, yes.
That's for though. Why is there 3 lines?
That's a definition. That means it's a definition. It's not.
You learned something new today.
It means it's defined as, right?
Life lesson.
You learned, that's all you learned today? Most of the time in the lab, most of the stuff you guys do, all the stuff you guys do, the pressure is constant. The pressure doesn't change of any system, right? So if that's true, then we can say this. All I've done is I've taken the pressures outside of the change in sign, because it's not changing, it's constant, right? It's constant. So what this tells us is that the change in enthalpy, and enthalpy is this made-up function that's just nice to use, and I'll show you why in a moment. Where an enthalpy, this is the definition, in internal energy plus PV. The change in enthalpy for any process is equal to the change in internal energy plus P delta V, pressure times the change in volume. If it's a chemical reaction we're talking about, we're not going to measure directly the enthalpies of any products or reactants, but this is what it means. The form we'll use is this. So I'm just going to take that last equation I wrote, and instead of delta U, I'm going to write the definition of delta U over here, Q plus W. Okay? That's the delta U part plus P delta V. You guys see what I did there? But we know what W is, right? I defined that for you guys a few minutes ago. I'm going to substitute that. That you get it good, okay? So that means P delta V's cancel, right? It's just Q of reaction. All of this is at constant pressure. The convention that we use is that if it's at constant pressure, we use a sub P instead of the reaction. Say this. And so, ultimately, this is what the change in enthalpy is if it's constant pressure. You can talk about change in enthalpy when it's not, pressure's not constant. We won't, but you can do it. And so what this tells us is that when the pressure's constant, the change in enthalpy is just the heat, the amount of thermal energy that's transferred. And that's something we can measure easily by sticking a thermometer in it. So for the lab that you guys are doing this week, part C, you know where you're mixing the acids and the bases? You're measuring the temperature change, right? That's Q. That's the amount of thermal energy transferred. that's equal to the change in enthalpy for that reaction. That's why we're, that's why I said delta H is equal to my energy transfer. That's something that we can look up in tables. Thermochemical equations, one where you have a regular chemical equation, and then after it you show the change in enthalpy for that reaction, delta H. Let's see if that's, this is a fun one to do. That's an example of a thermochemical equation. And you have to be careful that you understand exactly what that number means. I don't write kilojoules per mole. Sometimes you'll see that, right? But what this says, okay, first of all, the negative sign means that this much energy is released when 2 moles of hydrogen combine with 1 mole of oxygen to make 2 moles of gaseous water. Okay? So this is really per 2 moles of water produced, per 2 moles of hydrogen that reacts, or per 1 mole of oxygen that reacts. You guys see that? Now, it ends up that the enthalpy change for any process depends upon the conditions under which that process happens. What temperature is it? What's the pressure? All these things, right? That makes it hard to tabulate. So what we do is we've set up what we call standard conditions. Standard conditions are, generally the pressure is 1 bar. Everything's in there is a pure substance. If it's a solute in a solution, then it's 1 molar. Okay? And it depends upon the temperature. So usually we specify the temperature. Commonly you'll see 25 Celsius. That's a pretty common temperature to calculate. So standard states. And this, we show that we're talking about standard states with a superscript 0 after that. That's what we mean by the standard states. And the superscript 0 means standard states. The only property, only function we've seen, is we just introduced is the enthalpy, the change in enthalpy. But there are other properties you'll see in 102. Entropy gives free energy, and you're gonna see those tabulated under standard conditions also. So that's what the superscript O means actually. Let's do an example.
Yeah. Just make sure you study. What do you guys think? Absolutely, we have to be doing that. But the big picture, right? Ultimately, what's kind of like our last calculation that we're going to do? To get our answer, what am I asking? The change in enthalpy for the reaction, the heat, right? The change in, and it's negative, so it's going to be evolved, right? How much heat's involved. So what this thermochemical equation tells you is 896.3 kilojoules are released when 2 moles of this react with 2 moles of nitric oxide. This is hydrozoic acid, by the way. What I want to know is when we have 21 grams of hydrozoic acid and that much nitric oxide, how much energy is actually released, right? So we know that this. guys see that? That's what that thermochemical equation tells us. So what that means is, okay, these are conversion factors. For every 2 moles of hydroxylic acid, we make this many kilojoules. For every 2 moles of nitric oxide, we make this many kilojoules. So which one are we going to use? I mean, it ends up, that it's only 2 here, but we have different moles of each, right? Probably. How are we going to figure out which one to use?
Limiting reactant.
Limiting reactant, right? Right? So back to that same old stoichiometry. Right? When you're given amounts of both reactants, use the limiting reactant as your starting point, right? So all we have to do is find the limiting reactant, see how many moles of it we have, and just use whichever conversion factor we need. Right? One of these two. Does that make sense? So our goal, our first goal then, is to find out what the limiting reactant is. Once we do that, we can use the moles of that to find out how much energy is released. So to find the limiting reactant, remember the way that I showed you guys how to do it is you find moles of each reactant, then divide by their coefficients. The smallest number is the limiting reactant after that. So, gave you grams. To go from grams to moles, use the mole mass, right? About 43 grams per mole, right? How are we going to find moles of the nitric oxide?
Concentration.
What phase is it? Can you read my writings?
Yes.
Gas, right? That help? How are we going to find out how many moles of nitric oxide? We just did this chapter, right? What did I tell you about nitric oxide? Here, what information did I give you?
Liters.
Which is a volume. What else did I give you?
Molar.
Pressure, temperature. What does that bring to mind? Pressure, volume, temperature? Right?
Ideal gas.
EV equals nRT, right? Right, yes? Yes, I know you did. She's like, yeah. You have to get the right units, right? So, what R do you want to use? Bar? Okay, go ahead. Volume, it's already in liters. Of course, I put that in the wrong place, didn't I? Let me make this 3 Steve, right? You guys get the same number? So, the next step would be to divide by the coefficient, but the coefficients are the same, right? So that means whichever one of these numbers is the smallest, that's going to be the limiting reactant. You guys buy that? Which means that the nitric oxide is the limiting reactant. So all we have to do now is take the moles of the limiting reactant times this. Use this conversion factor. Does that make sense to you? See why we're dividing by 2? A lot of people forget that at first. They just want to multiply by the number of kilojoules. But it's this thermochemical equation tells us that there are 896.3 kilojoules released for every 2 moles, per every 2 moles of nitric oxide, right? So that's what this is saying right here. Is that okay?
So you don't consider the moles of whatever acid that is?
Yeah. No, because it's not limiting reactant.
Okay, but it doesn't still have energy?
Sure. This much energy for 2 moles of that, right? But we had this many moles of the hydroxylic acid.
Yeah. Yeah, I know. I thought you'd take out the 2 because you also have the energy for the acid as well. So you have. Do you understand what I'm saying? It's like you have the energy of the.
You're still thinking limiting reactant. So divide by 2, right? To get the limiting reactant, divide by the coefficients.
No, I was saying because. Never mind. Just go forward with it. Honestly, I'll see.
Well, I'm pretty much done.
Oh, okay.
So you got?
No, I didn't get that.
Did you divide?
Negative 7.
I got
You didn't get that same number you
negative
had.
37.06.
Negative 37, right?
Yeah.
I like this.
That's why I asked you guys to. So let's talk about what it means, right? We know that 896.3 kilojoules are released when 2 moles of nitric oxide and 2 moles of hydroxylic acid react. But we don't have 2 moles of each. We have 0.08 moles of nitric oxide and 0.488 moles of hydroxylic acid. So the reaction is going to stop after we run out of the limiting reactant, right? Which means that really what's happening is 0.08269 moles of nitric oxide are reacting with 0.08269 moles of hydroxylic acid. And the rest of the hydroxylic acid's not reacting, it's just staying there. So the energy that comes out of the reaction between the nitric oxide and the hydroxylic acid is this much.
Yeah, it makes sense. I was just confused because I thought if you have the hydroxylic acid and the nitrous oxide, nitric oxide, it would be twice that because it's the energy from the nitric oxide and the hydroxylic acid.
No, this is the energy from both of those. That's already taken into account.
All right, thanks.
The rest of you guys all right with this? Just gonna do this.
Now let's compare change in internal energy versus the change in enthalpy. The difference between the two is going to be this term right here, right? It's a gas reacting. First of all, let's look at an example. Oh, let's look at the one we just did. Back up. Change in volume for this is the volume of the products minus the volume of the reactants, right? In this case, it's going to be the volume of hydrogen peroxide plus nitrogen minus volume of the hydrozoic plus the volume of the nitric oxide. The volume of the gas is a lot greater than the volume of a liquid. Usually for, in the same conditions, same number of moles, it's like 1,700 times greater, right? It's like just so much more greater. Which means that we can neglect the volume of the liquids or the solids in this and just look at the gases. That means approximately, right? It's supposed to be a wiggly sign. That's just a change in the volume of the gases. But we have pressure times a change in the volume of the gases. That's just equal to PV's nRT, right? So P delta V is going to be the change in the number of moles of gases times RT, where there's no delta in here because temperature is constant and R is constant. You guys buy this?
Yeah.
Yeah? All right. Well, for this equation right here, the change in volume of gases, okay, would just be the change in the moles of the gases, basically, which would be 4 minus 2. It's just the change in the coefficients. What do you think of that? Not sure.
if I can write this. Is that all right? Where all we're doing here is we're ignoring the change in volume of any liquid or solid because the volume and change in a liquid or solid is going to be negligible compared to any gases, right?
The delta N gas that we're in last on the bottom is equal to delta V gas.
Where, yeah, delta nu, yeah, it doesn't matter.
That's a big one.
What's that? Yeah, it doesn't matter. It just means that's a nu. But all it stands for is the sum of the coefficients of the gaseous products minus the sums of the coefficients of the gaseous reactants. Which is these numbers right here, right? So what was that, 96?
96.33.
So the change in enthalpy for this reaction, okay, that is for 2 moles of hydrozoic acid plus 2 moles of nitric oxide to make 1 mole of hydrogen peroxide and 4 moles of nitrogen gas, is that much, which is equal to the change in internal energy for that reaction plus the change in the moles of gas. Okay? As written, that means 2 moles of hydrozoic acid plus 2 moles of nitric oxide, making 1 mole of hydrogen peroxide and 4 moles of nitrogen. So the change in the number of moles for this delta H is going to be the moles of the products minus the moles of the reactants. Right? Do you guys buy that? Kind of. The change in moles of gases, okay, so our delta change in N for gas, right? You got this from P equals nRT. It's just going to be the change in the moles, the coefficients of the products that are gas minus the coefficients of the products that are reactants. So for this reaction as written, 896.3 kilojoules is the delta H when 4 moles of nitrogen gas are formed and 2 moles of nitric oxide react. That's the change in delta N for the gases for that amount of energy. You guys buy that? So that's all I'm saying right here. Okay? It doesn't matter what the symbol is to nu, but the change in moles of gas is just a change in the coefficients. It's really easy. It's 4 minus 2 in this case, right? Okay, you guys are up with that? I have time. I guess I'll pick up right here.